Section 4-9 is on related rates, and the objective for this section, remember, is given a problem in which several quantities vary, predict the rate at which one of them is changing when you know the other rates. And again, the term related rates comes from the idea that we are coming up with a relationship between rates, and the way that we get that relationship is we're going to start out with an equation that involves a couple of variables. We'll then take a derivative of that with respect to t, our time, and thus we'll get a relationship between some rates. All right, so let's take a look at another example of a related rates problem. Example 2 says, suppose you are drinking root beer from a conical paper cup. The cup has a diameter of 8 centimeters and has a depth of 10 centimeters. As you suck on the straw, root beer leaves the cup at a rate of 7 cubic centimeters per second. And it says, at what rate is the level of the liquid in the cup changing? For part A, it's when the liquid is 6 centimeters deep, and for part B, at the instant when the last drop leaves the cup. All right, so let's draw a sketch of this. They gave you a sketch there to work with, but I'm going to draw another sketch of it here. And so let's say that this is our conical cup. And they told you that the size of this cup, it has a diameter of 8 centimeters, and it has a depth there of 10 centimeters. All right, and you've got some sort of a liquid in this cup, so let's say that that liquid has, I don't know, about this level right here. So then the liquid itself in the cup, if I measure this distance there, we'll call that distance h. Of course, that's changing because as you drink more out of the cup, that height is changing. And the radius, we'll say, is this distance right here. And again, as the level of the liquid in the cup changes, the radius is also changing there. So you got the radius and the height there. All right, so let's write down what we know and what we're trying to find in terms of rates. So they gave you one rate, and that was the 7 cubic centimeters per second. It says root beer leaves the cup at that rate. So again, if you look at the units, it kind of helps you see what kind of rate it is. Cubic centimeters would be measuring volume per second. That's measuring time. So that must be dV dt that we're looking at there. It's equal to 7 cubic centimeters per second. All right, and it also says that root beer is leaving the cup at that rate. So in other words, the volume is decreasing. So this is actually a negative 7 cubic centimeters per second for that rate. And then let's write down what we're trying to find. And again, be careful with that value that we wrote down that we know. Again, they will not usually tell you. It'll be very rare that they tell you that it's negative. You have to always go back and consider, is that a positive or negative rate they have told us there. But as far as the question here, it says at what rate is the level of the liquid in the cup changing? So the level is talking about the height of this liquid. So that's dH dt. So we're trying to find dH dt, and there's two parts to this one. They say find the rate at which the level of the liquid in the cup is changing when the liquid is 6 centimeters deep. So they want us to do this for two parts here, when H is equal to 6 centimeters. And the other part of it, it says at the instant when the last drop leaves the cup. Well, when the last drop leaves the cup, H is going to be equal to 0 centimeters. So there's two parts there that we're going to have to find at those two values there. All right. So the first thing I need to do is come up with an equation that relates volume and the height of this liquid. So I know that the volume of a cone, and I guess actually they, no, they didn't remind you in this problem, but that's a formula that we should perhaps know. They would have been nice, I guess, for them to remind us what the volume of a cone is, but nonetheless, it's 1/3 pi times the radius squared times the height. So there's our volume of a cone. But the problem with this is the fact that I've got this in terms of volume, radius, and height. So I need a relationship between radius and height and volume, whatever the case it might be, so I can get rid of the radius in the problem. I know dV dt and I want to find dH dt, but I don't know anything about dr dt. So I don't want that in the problem here. So we're going to go back to our sketch over here. and look at another way that we can come up with that. Because I know the dimensions of this original cup here, if I were to put this in the XY coordinate plane, and we'll put the X and Y axes right here, so the vertex of that cone is right at the origin, then it turns out that this point right here in the XY coordinate plane that has an X value of R actually and a Y value of H, the radius and height of that liquid. In fact, that point falls right on this straight line right here that goes through a couple of other points that I know. It goes through the origin, first of all, that's at 0, 0. And it goes through this point up here, which is at the very top corner there of my cup. And that has a radius there of 4 centimeters and a height of 10 centimeters. Again, the 8 centimeters was the diameter. The 4 centimeters is the radius, really, of that original cup. Now, this is one way we'll be able to come up with a relationship between R and H here. You could also look at similar triangles. Similar triangle between the liquid in the cup versus the entire cup. You'd come up with a similar equation. They're actually the same equation. But I'm just going to come up with the equation that I have here. So R and H I can write in terms of, I can write H in terms of R here, just like I could if I was given 2 points on a straight line and asked to find the equation of that. Here it's going to be in terms of R and H though. So H is equal to the slope of this thing. It's going to be the change in the y's over the change in the x's. So the change in the y's, it's 10 minus 0 over 4 minus 0. So the slope there is 10/4 times your variable, which is R, plus your y-intercept, which is 0. So that's our y equals mx plus b, if you will, or in our case it's h equals 10/4 r plus 0. And we want to know what r is equal to, so I'm going to solve this for r. So r would be 4/10, so that would be 2/5 of h. So now I have a relationship between r and h. I can replace r in my equation over here. Volume is equal to 1/3 pi times, instead of r, it's going to be 2/5 h, and that's squared. The radius is squared times the height. And let's simplify this equation before we start taking the derivative of this thing. So we have 1/3 pi. When I square the 2/5 h, I'll get 4 over 25 times h squared times h. And let's just rewrite that one more time here. Let's put this whole constant part together here. I end up with, I guess I'll write it as 4 over 75 pi. That's a constant, 4 pi over 75, or 4 over 75 pi, times h cubed. There we go. So now I just have a constant times my function there on the right side. So we want to take the derivative of this thing with respect to time. And on the left side here, this is where we get our dv dt. We know dv dt. They told us that. And on the right side, we have a constant. That's 4 over 75 pi times our function. Derivative of h cubed is 3h squared times dh dt. Again, following chain rule when you take that derivative. And we are looking for this value of dh dt, so I guess we can solve for that, or maybe actually one thing we should do here. The 3 over 75 here would end up being 1 over 25, so we can simplify that a little bit. But if we solve this for dh dt, I'll put it over on the left side here. dh dt, I'll divide by this whole thing here, really, to move it to the other side, I guess. It turns out to be dv dt. Well, let me write it as 1 over all this stuff, and then I can put the dv dt at the end. So 1 over 4 over 25 pi times h squared times the dv dt. Okay. So dv dt. Let me try rewriting that. There we go. All right, and so they asked us to evaluate this at 2 different places. Part A was when h was equal to, that was equal to 6 centimeters. So when h is equal to 6 centimeters, dh dt is going to be equal to, it's going to be 1 over 4 over 25 pi times h squared. That's going to be the 6 squared. And we know dv dt, remember, let me scroll back up there to the top, what we knew. We knew that dv dt was a negative 7. So this guy here is a negative 7. And I guess we can simplify this here just a little bit, or at least rewrite it a little bit. 6 squared here is 36 times 4 is what? 36 times 4. Let me just punch that in my calculator here. Is 144. So I guess I can write this as 1 over 144 over 25 pi. And I can multiply by the negative 7, or actually I'll put the negative 7 in the numerator, so it's a negative 7 over that. And if we simplify that, I guess just to get a decimal approximation for that, if we take negative 7 divided by the 144 over 25 times pi, we get negative 0.387. Negative 0.387. Oops, negative 0.387. And that's in the change in h over the change in time. So h is measured in centimeters, or the change in time is seconds. So that's centimeters per second. Okay, if you want to leave it in terms of pi like we had up above, you could do that, but just give us an approximation here, and as far as a decimal is concerned, we had a negative 0.387. So that means that when the height is 6 centimeters, the height is dropping at about 0.38, almost 0.4 centimeters per second. All right, take a look at part B now. Part B of this said do the same thing, but now when the last drop leaves the cup, at the instant when the last drop leaves the cup. So that's when h was equal to 0. So at h equals 0, let's write down what dh dt is equal to. It's again 1 divided by, let me scroll up to remember what that formula was. It was 1 divided by 4 over 25 pi times h, which is 0 squared, times the negative 7. You can see we're going to run into a problem there because we're dividing by 0. So this is undefined, or in other words, it's really a constant divided by 0, which you could say that's infinitely fast here, but this is undefined. And so at the moment when the last drop leaves the cup, this thing is going faster and faster and faster is what's happening, and it's actually going infinitely fast there as that height actually gets closer and closer to 0. The denominator of this quotient here is getting smaller and smaller and smaller, so therefore the quotient itself is getting bigger and bigger and bigger. So it becomes undefined. All right, that's the only example we need to cover here in this section, in the last part of this section here.